Swayam Prabha. Digital India. Educated India.
In the last class, we started discussing problem of grip in a tire. The fundamental aspect that gives grip to the tire is its interaction between with the road, and that it develops what we called as the frictional resistance to its motion. Now let us understand this from two perspectives. We've started this already. One is from the elastomer perspective. How does elastomer function when it contacts the road? And the other from the road roughness perspective or the road perspective. So there are these two things we have to understand, because after all it's the interaction between these two which results in what we call as grip. Just to summarize what we did about the elastomers, we said that the elastomers are basically elastic viscoelastic material. In simple terms, they are viscoelastic materials. We said that there are two things that have an effect. One is the frequency and the other is the temperature. And in fact, we saw that they have an opposite effect, and we determined or we explained that the region where, say for example, an elastomer operates can be divided into three parts, and that you have a region where it is, say for example, this would be the frequency. We said the region where the frequency is low, the elastomer acts like a spring, right? And in another region where the frequencies are very high, it becomes very rigid. Okay, so it becomes something like a very rigid part, essentially because it has to slide back to its original position, and the sliding back is affected by the interaction of these long chain molecules, macromolecules, with others which are present, and hence it becomes rigid. And between the two regions we have the viscoelastic part. We said that the graph for the modulus goes like that, and because there is a viscoelastic part at the center, if I now plot the energy that is consumed due to deformations, then it would go something like that. Right. This we said is the glass, corresponds to the glass transition temperature. Okay. So if I now put the temperature here, we said that this whole graph goes in the opposite direction, and that what happens at higher frequencies happens at lower temperature, and so on. Okay? So this is what we said yesterday. We said that there's a relationship between the two, and is given by Williams, Landau, and Ferri WLF equation. This equation gives a shift, say in for a frequency, when you shift the temperatures. When there's a shift in temperature, you would see that there's a shift in frequency as well. Okay. So We will come to that in a minute. Just summarize what all we said yesterday, the last class. And we also said that there is a lag between the applied force and the deformation, or in other words, applied stress and the strain that is developed. Okay, there's a lag between the two. So if I now plot, for example, the stress and then plot the strain, okay, develops is something like this, and that there is a phase lag between the stress and the strain given by the equation delta or tan delta is an important quantity in the study of viscoelastic materials. In your classes on vibration, you would have studied about, or in controls, you would have studied about phase lag, and so on. Okay, and you would have expressed the quantities of interest in a complex plane. Okay, the complex plane is essentially used in order to bring out this kind of phase information. Hence, here we have what is called as a complex modulus for a viscoelastic material, which consists of a real part, which is called as the storage modulus, plus an imaginary part, which is called as the loss modulus. Note that there is nothing imaginary in this. The only thing is that we express the phase information through a complex quantity and call that complex quantity into real and imaginary. Right. You can say that this tan delta is an important quantity basically because that gives you the amount of energy that is dissipated. So in other words, tan delta, which is from here you can find out what is delta. Tan delta can be written as energy dissipated. So when there is a loading unloading, there is an energy that is dissipated and can be looked at as a ratio of energy dissipated to the energy stored. So tan delta becomes an important quantity which tells us about the dissipation of energy. So if you now plot, so what does it essentially mean? If you now plot, say for example, omega versus all these three quantities, which is E prime, E double prime and tan delta, the graphs would look something like this. We've already seen how E prime would look. So E prime would look like that. That would be the E prime value. E double prime would look something like this. That would be the E double prime value. And tan delta would be something like that. That will be the tan delta value. This is at one temperature. So this temperature is a constant here. If I want to determine this at any other temperature, it's not necessary that you have to keep on applying the same set of experiment or do the same set of experiments. That's not necessary. Okay, this whole graph gets shifted depending upon the temperature. This whole graph gets shifted. In other words, if I have data at one temperature here with respect to frequency, I can find out the data with another temperature by shifting this frequency. In other words, shifting this graph. In other words, at t what happens at omega and at temperature T, if I now shift the temperature to T plus delta T, then what was happening at omega would happen at omega plus delta omega. This shift, okay, can be determined from the WLF equation, which is given something like this. Log of AT, the shift, is given by C1. This depends, so you can write this as C1 into T1 minus T naught divided by C1 plus T minus T naught, where C2 into T minus T naught, where C1 is equal to minus 8.86. Usually, I mean, it's not, it varies, and C2 is 101.5. T naught is the reference temperature. Okay, and which is say the glass transition temperature plus about 50 degrees. Right. Now, glass transition temperature itself depends upon the frequency. So, when I shift the frequency, that temperature, glass transition temperature also shifts. Now, how do we use this? Suppose I have the data to be, or data recorded at omega and T, okay, and I want to determine what would be the this data, say at a temperature, say Tc, okay, then what I have to do is to find out the shift, say let me call that as Q, which is log of AT minus log of ATC, and shift the frequency, and this is of course given in log, so shift the frequency to that decade frequency. Okay, so each data point that is obtained in omega T, okay, that is this experiment. Okay, now you say, for example, you are plotting this graph of log omega versus, here if you have log omega versus the value, say E prime or E double prime and so on, okay, and you want to find out what would happen to in the new temperature, then you shift this a point, say for the new temperature, by this much amount, by that much amount. So this is the shift factor. In other words, this shift factor is the relationship between the temperature and the frequency. Any questions?
So if you're increasing the frequency, temperature will, the cancel temperature will shift.
Yes. So depending upon, that's this relationship. So what happens, what is the relationship between frequency and temperature? So what happens at lower temperature happens at higher frequency. Okay, so that is understood, correct? So this is just a mathematical expression for this shift, right? So usually one decay, that is if there is a one order of magnitude in the frequency, would result in a shift of say 6 to 7 degrees is the shift. You know, that's what would happen. Okay, that's the first part.
What does AT signify?
That is the shift. That's the shift. So the shift is calculated by this formula. So WLF gives you actually the relationship of shift, or relationship between frequency and the temperature. Okay, so that's what I explained now with respect to Q. It is, in other words, what it simply means is that I can do all the experiment at a temperature, at a particular temperature, and call this as a master curve. And then I want it at any other temperature. Okay, I can do that. I can determine that not by repeating an experiment, but by using this kind of shift factors. So that's what WLF tells us. Okay, that's a property which we will. T naught is the reference temperature, which is usually T1 is the temperature, or T rather, not T, where the temperature at which I am determining the AT. Now let us.
There is limitations for this temperature. To estimate, we can use this formula.
That depends upon, see, what is the value of C1, you know, where do you apply, all these things depends upon the elastomer in question. Okay, for usually this is applicable for the range of interest for what we have, right? So 10 to the power of, say, suppose I have a 10 to the power of 1 in the frequency or 10 to the power of -1, I want 10 to the power of 5, it's possible to do that. Before we go further, let us look at the frequencies of interest. Then we will understand how we can apply this. So let's understand what are the frequencies of interest. In order to do that, we have to now look at the road. So this is the elastomer behavior. We'll now shift to the road, right? Okay. Because this friction is going to be very important, and the friction is very different from what you see in metals. So it's important that we understand how it works. Okay, now we shift to the road, and we're going to look at the road from two perspectives. One, in a macro perspective, okay? So the road looks, say, let's say that something like this. It's not that as big as this. Let's say that that is about 1 centimeter is this, 1, 2, in terms of centimeters. This is, what is this? This is those gravel stones which are sticking out as you see it in the road. Okay, so there's a binder between them. Okay, the asphalt binder is what binds this kind of stone. So these are the stones. This is at a macro level. If you now go and look at the stone more carefully, you have also small undulations or small micro roughness, which you would call as something like that. Micro roughness. Okay, so these are the two things how actually a road is can be looked at. A macro, which can be in terms of a centimeter or so, and micro in terms of a few microns, which can at the maximum be 0.1 millimeters. That is, this roughness is of the order of, say, 0.1, maximum of 0.1 millimeter, much less 0.01 millimeter, and so on. A few microns to maximum of 100 microns. Right? Okay, this is how you look at the road. What does rubber do? Or what does the tire, as it contacts the road, what does it do? It actually engulfs the whole road. So you can see that that would how, say, a tread block would look like. So it engulfs the road, right? So because the deformations are quite large, it just goes and sits over this gravel or the stone, right? Now what happens? Two forces are exerted. One is the force which is normal force. On the other, say, let us say that traction, braking, whatever it is, a tangential force. Okay? These are the two things that act on this block. Now, again, there are two things that happen. One is the micro-macro, the other is two forces, and there are two phenomena that happens between the rubber, the block, and the road. the phenomena can be classified into what is called as hysteresis and molecular addition or addition. You can call this as molecular addition. Okay? So molecular addition again happens at a very small length scales, and hysteresis happens at a much larger length scales. Right. Okay. So let's quickly look at this, because then we will go there and understand this. What is meant by what do we mean by this addition? Actually, these long chain molecules, which we represented by means of a simple model of spring and dashboard, these long chain molecules get attached to the surface, assuming right now that the surface is dry. It gets attached to the surface through what? Van der Waals forces, or Van der Waals bond is what is formed between these long chain molecules and the surface. So they form this bond. Let us say that this is a rubber piece. Okay? They form a bond with the surface molecules, or the surfaces that exist, right, the surface. And then when they are subjected to a force, these bonds that are present here, it breaks. So it sticks, breaks, slips, then again sticks, breaks, slips, and so on. So at the addition, at the molecular addition level, there is a sticking, slipping, sticking, slipping, and so on. So it is the Van der Waals bond that forms, breaks, forms, breaks, and so on. Right. But what happens here? What is this hysteresis, and what happens here? That's a very interesting phenomena. And we already know that when a rubber piece is subjected to loading and unloading, it loses energy through this phenomena of hysteresis. Okay. Now, let's say that for a moment, forget about that. We have normal forces. Obviously, the normal force would give rise to a contact pressure, which would act something like this. Which would act something like that. Now, when there is a lateral force that this block is subjected to, then obviously this kind of symmetric distribution, okay, which equilibrates the normal force, is no more maintained, and this pressure distribution becomes unsymmetric, because it has to now equilibrate that lateral force as well. So what was nice like this, which was equilibrating this, would also have a force which has to equilibrate this, and hence the vectorial sum of these two forces would be something like that, and with the result that the pressure distribution now shifts. Superpose this onto these two phenomena. What really happens at this point is that there is a slip. Okay, there is a slip, and this whole block can move out of this hill, okay, and slide down. In other words, the loaded region, don't look at it as this big. We are talking about this whole distance itself is 1 centimeter, like maximum of 1 centimeter, right? So keep that in mind. So what happens is that this slips, it goes over the hill and slips. So when it goes like that, what was loaded becomes unloaded. Okay? So when it slips, it may again get reloaded and so on. So the frequency of loading, unloading, because of this kind of macro pieces, okay, depends upon the velocity of sliding and is given by simple V by D, the distance between the two. This I would call this as D, then V by D is that frequency with which this slips. The frequency with which that stick slip happens is much less. So if this is around 10 to the power of 4, this would be actually 10 to the power of 8. So that's the frequency at which it slips. So in other words, there are two things that contribute to what we call as friction. There are two things that contribute to what we call as friction. One is the hysteresis loss, and the other is this kind of micromolecular interactions. So that energy is what gets converted into a frictional resistance in rubber and can be written in a very simple form as the friction forces, or the friction coefficient if you want, can be divided into two categories, one due to addition and the other due to hysteresis. Right? So we can call this, or we can quantify this by means of a simple equation. This is by Moore in his very good book on friction of rubber. There's a book on pneumatic tires, very early book, very good book. So I'm taking this from there. So that's the reference. So that is given by addition, and let me write down that carefully. K1 into S into E prime by P power R into tan delta, and mu hysteresis is equal to K2 into P divided by E prime N into tan delta. S being the effective shear strength. S is the effective shear strength of the material. P is the pressure that's acting, okay, the normal pressure that's acting. Exponent R is usually about 0.2 and N is greater than or equal to 1. Okay, so essentially friction is the result of these two. In order to put this in proper perspective, we'll go a bit back and forth so that we get a macro picture of the whole tire. We are going to we are going to molecular level. We'll look at the length scales again when we summarize. But what I want you to understand is that this is happening in a rolling tire. That's phenomenal. So a rolling tire, okay, is subjected to this kind of phenomenon. So as it rolls, let's say that these are the tread blocks, okay, that's the carcass, okay, on which we have what are called tread blocks. We saw that yesterday. So these tread blocks go through that kind of cycle, that kind of, engulfs the stones that are there, gravel that are there. They develop a bond between the surfaces. All these things happen when this whole tire rolls. So that's very interesting. You can look at how fast that's going to happen. Okay? So in order to get again a macro picture from a tire perspective, let us see what happens, and then again we'll come back here. Right? So let's see what happens in a tire. Let us now consider a tire again, in isolation, and then tie up. After we finish that, we'll tie up the concepts that we have explained now with the tire. The very first thing that we notice in a tire, pneumatic tire, is that a tire which is like this, let's say that it's an inflated condition, okay, gets deformed or is deformed when I apply a load and put it on the road, okay, and when it rolls, this deformation again takes place, obviously. So in other words, there are different radiuses that are present, okay, in the tire. One is this free radius, okay. Now, because it gets deformed here, the free radius is not maintained, and hence you have at this point, we'll call this as loaded radius, okay. So I have a free radius R. Let's say that that's a loaded radius RL, and in between the two, what you do not see here is what is called as a effective radius RE. What is effective radius? Very simple. If this guy is not to be deformed, and it just rotates with a angular velocity omega, then the tangential velocity v is given by omega into r. Right. So, in other words, as the wheel rotates with an angular velocity omega, and the wheel travels with a longitudinal velocity v, then v is given by omega into re. So re is defined with the same formula that you are all familiar with from fundamental dynamics. Right. Before we go further, let us understand this contact patch. Okay. From a plan view, let's say that the contact patch looks like this. There's a lot of niceties in this. We will come to that a bit later. Let's say that that's the contact patch. First things first. When the tire is stationary, like that, it's not, omega is not there. So when this, I'm saying that this is stationary, then you have a contact patch, of course, the region where the tire is in contact with the road. Okay. There are different points on the tire which sit at different point on the road. So all these guys sit in different points of the road. Right. Very simple to understand, nothing very difficult. On the other hand, let us see what happens to the contact patch as the tire rolls. Okay. In order to understand that, let's do a small thought experiment. Okay, and the thought experiment is necessary to dispel some of the ideas which you may have, which I have over the years students asked. Okay, so we are going to do this thought experiment. Let's say that these are the threads or the bristles that are sticking out, right? So let's say that you're going to sit there. Okay, don't worry, this is only a thought experiment, you're not going to be hurt, just sit there. Ask your friend to go and sit at this place. Okay, and another friend who sits here. Now the tire rolls, right? So as the tire rolls, what happens? You would go and hit the ground, right? You would go and hit the ground. So the new situation would be like this. Sorry, let's say. So you would have hit the ground here in this region. Okay, let me just extend it. So it's not that you're going to become zero. So you will get compressed, right? So you will be at this position. You're just going to hit the ground. The first thing is that you are not going to travel in space like this. You are not going to travel in space like this. Then what happens? So you hit here. Let's say that you're not slipping. You're just your forces are such that addition is such that you're going to stick there. Then what would happen? Your friend who's sitting here, that guy would hit the ground before you. Okay? Then the other friend, he will hit the ground before that guy. So in other words, you can imagine that the contact patch is actually traveling over you. It is not that you travel over the contact patch, but the contact patch travels over you, because as new guys keep hitting, relatively you would be moving back in the contact patch. So in other words, what happens is I'll hit here, I'll stand here, there's another guy goes there, someone else, and so on. So with respect to the ground, with respect to the contact pressure, actually I'll be going behind. Okay? So ultimately, I will come to a situation where, because of this rolling, I'll come to a situation where I am at the end of the contact patch, I'll rise up and go out. Okay. Now, let's see what happens when you stick. You're subjected to a pressure. Okay? So you're subjected to a pressure. So let's draw that situation. Let's just take that out. Okay? You're there. You're subjected to a normal pressure. And let's say some force is applied, and you're also subjected to a tangential force, which becomes a shear stress, okay, and so on, right, or traction. Under these conditions, what actually happens? I'll go stick to the ground. As long as possible, I'll be at the place. Okay, I will be pulled, so I will be stretched, and so on. Okay, depending upon there is a braking or there is acceleration, I'll be shifted in the two directions, different directions. But I'll stick to my ground because I have already established my relationship with the ground, and he's a nice guy, he's holding me. Right? And at one point of time, I won't be able to stand there because of all these forces. Okay, I have to slip a bit. I'll just move. In other words, there's a micro slip. From here, I'll just move like that. It's a micro slip. Right? Then again, I'll be subjected to a contact force which will not be the same as what it was before. We will see that. So again I may stand here, right. So in other words, if at all I move in the contact patch, I move over very short distances, micro distance, micro slip, very short distances, right. I do not slide or go from here to here, okay. The contact patch, as I said, goes above me, and at the maximum I am going to just move like that. So the first thing that is important to understand is the motion of this contact patch. It's you are not moving in the contact patch is moving over you. Okay, that's the first lesson. Let's get back to the tire again, right? And let's see how actually the change in radius has an effect on the velocity. Okay, so that is my tire, and since I'm going to hit the ground, that's my ground. I can't penetrate the ground obviously, so I'll be like this. That is the free radius. What did we call as R naught? What is that? I think we should maintain. Let's call that as R naught, right? What did we? Let me call that as original radius. So that let me call that as R naught. If I change the symbol, please let me know so that I do not confuse you with various symbols. Let's say that the original or the undeformed radius R naught. So that's R naught. Let's say that the RE factor, what is RE? This is the equal, like we used RE, yeah, equivalent radius. Okay, that is smaller than this R naught. So let's say that is RE. And the loaded radius RL, right? Okay. Let us now look at what happens at the contact patch. We'll look at the physics and then we'll look at the actual values. Now, again a thought experiment. Go and sit here. My tangential velocity V, omega R naught, where omega is the angular velocity with which I am rotating, right. So there are three conditions that exist in the contact patch, right. What are these conditions? Three conditions are that there are situations where the radius is more than, so that would be the radius, would be more than RE or equal to R naught, more than RE but less than R naught, and lastly it will be less than RE. Or in other words, this is the actual case. In other words, R naught changes to a loaded radius RL and RE sits between the two, right. So there is a region, let's just take that line, this line. When I just hit it, I am R naught. Somewhere at this point, my radius is equal to RE, that is the point. And somewhere at this point or the center I am RL. Again as I go back I have RE, go out I am at R naught, just go out. So there is a continuous variation of radius from R naught back to R naught. Clear? Okay. Now, let us now look at the velocities. The velocity when at the tangential velocity here is omega R naught, right? V tangent, let me be very clear, so that you don't get confused. Let's say that that's the velocity with which the vehicle is moving. Either you can look at the velocity of travel V and a stationary ground, or you can say that the wheel is stationary and the ground is moving. Doesn't matter. It's a relative velocity. Ground is moving in the opposite direction. Doesn't matter. Okay. However, you want to imagine, you can do that and it's not going to make a difference. Now, obviously, this velocity, tangential velocity, will be more than the velocity of travel, which is equal to omega RE. So, in other words, here is a region where the tangential velocities are more than the velocity of travel V. We call that as more. Here exactly the same. From here to here, it is less. Here to here, it is more. Get up and go, you're back to or not. Oh, that's a complex situation. Imagine that this is happening as the tire rolls. The guy is really confused. Initially, he is happily coming, hitting the ground. Suddenly, he's slipping in one direction. Then he meets Ari, and again goes in the other direction. Then again comes back to a situation where he has to go the opposite direction. Wow. So, mechanics is very complex, and that's what makes tire mechanics very interesting, right? So, if you look at the direction, okay, you will see that they are in one direction up to this. From here to here, that will be in the other direction. From here to here, that will be in this direction, and it goes up. What are they? They are likely slip. An interesting point is that we just now saw that without that slip, there is no friction. So your friction concept has to now change, because friction is now contributed due to hysteresis. Okay, it's that energy loss as well as due to addition. So without slip, so it's an oxymoron, but it's actually like that. Without slip, there is no friction here. So the tread is subjected to a very complex phenomena at this position. Okay. When it breaks, the situation is very different. Added to this are some subtleties. What are the subtleties? We'll just mention the subtleties and stop it. So imagine that you're so tired standing there, getting hit all the time in the ground. Let us say that you're going to lie down there happily in a bed like this. Okay. Now lying in that bed, you're going to approach the ground. Hey, there is already a signal that ground is approaching. How? Because of this radius change, when you are here, okay, the circumference gets reduced or is reduced, okay, and you are going to feel that as you go near, you're going to shrink actually. Your bed is going to be compressed. So that's going to be compressed. So as you go in, you're going to get actually compressed. And as you go out, you're going to get elongated and go out. So In a circumferential sense, the radius change results in a circumferential change. So there's a compression, okay, more compression, tension, in the sense release of compression, back. Right? So what is that effect? And we'll see that in the next class.